And now we want to share the screen. Can you see my slides? So today we will go to the set of slides for the X87 floating point unit. Okay. Next lecture, inshallah, we will have two sets of slides, one for the interrupts and one for the input-output. Inshallah, بإذن الله, inshallah, we will finish this set of slides today. It's kind of some architecture and details about how the microprocessor can do floating point operations. It's kind of theoretical slides a little bit, so no real programming that we will go over for the theory. We will learn some of the programming in the lab, inshallah, for the floating point, but not in theory. So there is no programming for the theory. However, we will go through some example to explain how can we deal with this what we call a coprocessor, which is the X87 floating point unit. So our slides today are starting by explaining the concept. I think throughout the last maybe 3 lectures, we have shown how complex is the floating point representation, how to represent numbers in floating point, and accordingly the hardware to perform those mathematical operations for the floating point is not that easy. We can spend maybe one full course explaining one mathematical operation, addition, multiplication or division, or even addition and subtraction to explain the hardware. How to build a hardware for the floating point is really complex, and it needs a significant amount of work to be done and explanation. So we can spend one full course explaining the hardware to perform one mathematical operation in floating point. So accordingly, the microarchitectures engineers who designed the machine at that time, and even till nowadays, they have a kind of what we call the floating point unit. Previously and during the 80s and 90s, they have a full coprocessor to perform the floating point operation. So for the 8086 family of processors, we have what's called the coprocessor. The coprocessor is something attached to my main processor to perform the floating point operations. So I have a dedicated hardware to perform the floating point, and it is at that age, or at that time, 90s, the 80s and 90s, they call it a coprocessor. It's a kind of a dedicated hardware for that, or a separate processor for that. It has different names. Some designers call it the numerical processor extension, NPX. Some others call it numerical data processors, NPD. And recently, the name that is conventionally and widely used is the floating point unit. So in the late designs of the microprocessors of Intel processors or AMD, they call it floating point units. But since we was studying during this class the 8086 machine, so we will focus on its coprocessor at that time that is used for the floating point, which is called the 8087. So we have the 8086 main chip that actually do all of the operations, the integer operations, as we explained from the beginning of the semester till we started the floating point. And we have another processor, we call it coprocessor, called the 8087 for the floating point operations. The slide here, slide number 3, is actually showing you the compatibility between the different family members of the 8086 machines and their corresponding coprocessor in the floating point. So you can see here they change the names, they change the architecture, they go from one design to the next generation with a more advanced design. So each main processor has its counterpart coprocessor for the floating point operations, as you know. I don't want you to remember any of this. It's just for your information. I give you some information about the history, some information about how things have been done, but no need for memorizing any of this. I'm just giving you some history here. This slide number 4, is actually showing how the connections is being done between the different chips. So I have on the top here the chip for the 8086 processor, which is connected to the PIC, which is actually related to the interrupts and the communication with the input-output devices. INT stands for interrupt. We will explain the INT, inshallah, in the next lecture, in the last lecture of this course. And we have the chip for the clock generator. As a matter of fact, you know that we are dealing with a digital, with the DLD chips that is powered by, not powered, but controlled by the clock. It's synchronous sequential circuit. زي ما احنا متفقين صح كده؟ فwe has a clock generator that actually generates the clocks for both the chips, the 8086 integer unit and also the 8087 floating point unit. So there is a kind of handshaking happening between those two processors. The main processor is the 8086, and while you are executing your code here, if the 8086 have recognized that one of your instructions is actually a floating point instruction, it will send the instruction to the 8087 for the execution, and it will wait the 8087 to inform the 8086 that the execution have been done to continue fetching the code and execute for the next instruction. So you can intermingle here in your code. You may have some instructions floating point, some of them integer, some floating point, and so on. Integer going to the x86 and floating point going to the x87. Okay, who the maestro, the manager of all of this is the 8086 itself. Okay, so that's why we call the 8087 as the coprocessor. It's just a helper for whenever you encounter a floating point operation, it goes to it will be informed by the 8086 to go and execute this and then return back to me. This is actually the picture for the 8087, which is at that time they call it the NPX processor. We will not go into too much detail, but the layout of the chip here looks very similar to the layout of the 8086 that we may have explained before. Throughout this chapter, we want to go over a little bit about the architecture, which we already almost done. What are data types that is supported by the 8087, how to interface with the 8087, and some instructions and programming. We learned some of that. We will start actually by the last part, which is the instructions and the programming. Floating point unit, the X87, is compatible with the 8086, and it supports some, mainly the floating point. In some of its instructions, it supports integer operations in a very limited, narrow capacity, and this is actually to do kind of conversion between floating point and integer, not to really perform the operation with integers. They also support what's called the packed BCD. We will not discuss the BCD into that much details. It's seldomly used in any way, so we don't emphasize on that. Type, what kind of floating point standard is followed here for the 8087? It is the IEEE standard 754 that we have discussed throughout our previous 3 lectures. Okay, so it supports binary arithmetic floating point operations as the one that we have demonstrated for the addition and subtraction in the last lecture. Type. From the execution point of view, these are actually more pictures that shows the internal structure of the 8087 processor. We will not go into all of the details for the processor. However, we need to emphasize on some structures here inside the machine. We have what's called the data buffer that actually keeps some of the data. لا. Do we need to know any of these internal structures? لا. I give it to you just for an information. You don't have to memorize any of this. خلاص؟ تمام؟ Don't worry. Okay? We will not take this in the details, that too much details, but I just showing you the architecture just to see it, yani, to let you know. Okay, the most important thing that we will be covering is the registers of this machine and some of the key registers inside it. The bank of registers for the operations, for the operands, and also 2 main registers, which are the status register and the control register. Okay, there is a lot of details definitely how this processor is working and how it is doing handshaking and communicate with the main processor, but we will not go into details, that much details. I'm just giving you this as a little bit of a quick background. طيب. The 8087 execution flow is actually, as we indicate, it takes its instructions, or it takes its order for execution from the 8086. The 8086 is not doing a full decoding for the instructions. However, it will, once there is kind of identifier in the instruction to support the floating point, to indicate that this instruction is really belongs to the floating point unit. And once the x86 recognize that this is a floating point instruction, it will go directly and send the whole instruction to me, the x87, for decoding and execution, and send back a message that I am done with the execution, to allow the x86 to continue in its operations. Okay. What we really want to learn in the 8087 is this set of registers, or not all of them, even we will not describe them in full details. The most important thing is that the bank of registers for the operands. We have also what's called the status register. يبقى احنا عندنا the status register, the control register, the what's called the tag word register, last instruction pointer register, and the last data or operand pointer register. We have also what's called the opcode register that carries the opcode for the instruction for decoding. Okay, but these are the set of registers. We will go over them, maybe not all of them, but the most important and the critical ones, to get you an idea about how this processor is dealing with the registers, is dealing with the instructions, is dealing with the controlling and the status of the operations for the floating point. Right. These actually another picture that shows the layout of those key registers in the X87 machine. Okay, we have what's called the data registers, a bank of registers. So in the X86 we have bank of registers اللي هم كان through we access them through their names. كان اسمهم ايه؟ حد لسه فاكر؟ AX, BX, CX, DX. Okay, we have also some index registers, SI و DI. We have the SP و DP. مش كده ولا ايه؟ تمام؟ So here we don't have distinct registers for performing to carrying the data. We have here a bank of registers. اسمهم ايه؟ From FR0. They are just named here as R0 through R7, but they actually, when you go and access them, you have to use the name F for floating point. So you have to use the letter F, as we will see shortly, to access them. For the machine itself, they call it from R0 till R7. So how many of them? We have 8 data registers. Okay, as you can see here, they are carrying floating point numbers. So you can actually recognize that they are divided in each of those registers are divided into a mantissa, fractional mantissa, exponent, and sign. Okay, the number of registers are 8 from R0 till R7. Type. How many bits of those registers? Those are 80 bits registers. Each register is 80 bits. Okay, remember that for the X86 we have how many bits for each register? Can 16. Okay, most of the registers or all of the registers was 16 bits. The data registers here are 80 bits. Okay, right. What kind of representations of floating point they have, we will see that at the end of the slides, inshallah. But before we go into the representations, the floating point representations used here, we want also to shed some lights on a critical other registers inside the machine. اللي هم ايه بقى؟ control register, status register, tag register, last instruction pointer, or last data pointer. Okay. As you can see here, not all of the registers here have the same size. يعني الcontrol والstatus والtag are 16 registers. Okay, similar to the 8086. Last instruction pointer with last data pointer are 48 bits, and the opcode is 11 bits. Opcode 11 bits means how many floating point instructions I can have. The opcode register is the register that should carry the opcode of the floating point instructions, and it has 11 bits. So that means the ISA, the instruction set architecture here, can have up to only 11. Up to ايه بقى؟ بالظبط كده 2 to the power 11 اللي هو يديني كام؟ اللي هو يديني 2048 different opcodes that can be programmed for the floating point. This is definitely a huge number of instructions. Not all of this is being used. تمام كده؟ طيب. The most significant thing that we need to discuss here is the data registers. The registers here are not accessible through, or the conventional way to access them are not accessible as a unique distinct register. يعني I'm not adding in floating point R0 to R1 and put the result in R2 or something like this. This register is a bank of registers. Registers here is a bank, is actually a stack of registers. So the conventional way, the default way to access the data registers in floating point, you access them as if they are a stack. كلنا طبعا عارفين الستاك. What is a stack? Stack means I'm doing the operations through pushes and pops, and I have a pointer which we call the top of the stack. يبقى ده, this is different stack, different from the stack in the memory. This is not the stack segment in the memory. This is a stack of data registers in the floating point, for the floating point. Agree? Okay. This stack is growing backwardly. Originally, when I have this stack is empty, the pointer should point to the R7. Okay. And when it fills up, I have some pointer that actually point to the top of the stack, which will be decremented. El push will decrement, will pop will increment. Here I have the stack top that actually points to the current location of the stack for the registers. Here I'm accessing the registers relative to the top. Relative to the top. The top of the stack is called the ST0, and the previous one is called ST1, and the previous is called ST2, and so on. Some operations is doing push to the stack. When I push to the stack top is moved one place downward or backward or decremented. This automatically moves the top of the stack or rename the ST0 to a new location. هنا registers are being accessed as if they are a stack of registers. Okay? A stack of registers. How many registers are 8? Right. Instead of calling them with their names, with their real names, I am using the default is I have some register that carries me the top of the stack. And the top of the stack has a dynamic name. اسمه ST0. When I say in my instruction ST0, I am talking to the top of the stack. When I'm talking about ST1, that means this is the previous register to the top. ST2 is the previous one to the top, and so on. You get the idea? Loading operation here will decrement the top by one location and will start populating the new top of the stack. The top of the stack is carried in what we call the status register, as we will see shortly. Right? I'm just showing you here. Status register here is carrying, okay, a group of bits. They call them the top, TOP. And this actually, bits are pointing to the current location of the stack register, okay, or the register of the stack. How many bits for the top? نشوف النص صح ولا لا. How many bits for the top? How many bits for the top? How many bits for the top? Wrong answer. How many bits for the top? How many bits do I need for the top? أيوة كده 3 bits. ليه 3 bits؟ ليه 3 bits؟ ما احنا قلنا البنك بتاع الريجسترز هم كلهم كام ريجستر؟ هم كلهم 8. I have 8 registers. So the top of the stack is actually 3 bits that identify where is my top. So currently here, the top here have which value? شايفين الفاليو بتاع ده؟ كام دي؟ التوب هنا مشاور على مين؟ مشاور على ال R3، اوكي؟ اللي هو الرقم 3 اللي هو 110، اوكي؟ طب if I use the load instruction. What's the load instruction? It is the instruction to load data from the main memory to the floating point registers. Load instruction automatically doing a push into this stack of registers. يبقى automatically اللي هيحصل ايه؟ automatically the top of the stack will be decremented by 1, so it will have the value top يبقى have the value ايه؟ الدكتور علي حاططها هنا اهو 010, okay, and it will go read the data from the memory and put it into the register number R2. يبقى load instruction here, which is actually in the X86 we have the move instruction. Here we don't call it move, we call it load instruction. طيب الفلوتنج بوينت لود بتعمل ايه؟ بتديكريمنت التوب of the stack register inside the FPU data register stack, would decrement its top, load the data from the memory, put it into the type. After the load here, okay, where is the ST0 pointing? ST0, is it still pointing to R3 or it is moved to R2? Moved to R2. برافو كده. يبقى after the load instruction, when I have an instruction that using the ST0, okay, if I use the ST0 as a name, it is now the new top of the stack. يبقى ST is the dynamic naming for the registers. Okay. يبقى I have static naming of registers اللي هم from R0 to R7. ده static. And I have dynamic naming of register اللي هو ST0, ST1, ST2, ST3 وهكذا. Okay? يبقى if I do a load instruction, I am pushing into my register of the stack some register from the memory. I'm loading from memory, getting to the register. This is automatically will go and push, decrement the top, and automatically the ST0 is pointing to a new location. يبقى ايه؟ يبقى ST0 يبقى 0 دي is relative location. 0, 1, 2, 3 is relative location. Okay? And ST stands for stack pointer. Stack top. Stack top. طيب. يبقى many floating point instructions have several addressing modes and permits programmers to implicitly operate on the top of the stack or to explicitly operate on a specific register. يبقى هنا you have the two modes of operation. Either you particularly talking about the FR1, FR2, FR3, okay? So you are in particular talking about one specific register. And this is not the conventional way to do programming for floating point unit, okay? The regular is to deal with the stack as deal with the registers as a stack and use the relative addresses ST0, ST1, and so on. By the way, ST is the ST0 by default. When you use ST من غير brackets means you are talking about the ST0. Okay? But if you want to access ST1 or ST2 or ST3 or ST4, you have to put the brackets and indicate. Right. In order to demonstrate to you how can I use programming with the stack, just with the floating point, just to give you an idea about that, we will take the following example. So, can you see this instruction? And for example, if the top of the stack contains the value 110, that means F register, the FR3 is actually on the top of the stack. Okay? And assume that I have this instruction. Instruction اللي هنا الexample اللي احنا واخدينه اسمها ايه؟ اسمها F add. So can you see here? Can you recognize the difference between the floating point instructions and the integer instructions? It's all instructions for floating point has one suffix, one prefix letter, which is the letter F, to indicate that this is a floating point. Okay, so I have F add, F subtract, F multiply, and so on. So the letter F is always a prefix for the mnemonic of the instruction. تمام كده؟ طيب. I need here to add two registers. If I am using the conventional way of the stack address or the floating point, okay, I'm doing the F add between ST and ST2. ST, as we mentioned, it is the default is ST0. يبقى a floating point unit will go and check the top of the stack. We will find the top of the stack is at register FR3. Okay, ST0 is pointing here. Okay, the F add will go and read or will pop the value of ST0 from the register, will pop or will read the value for ST2 from the register, send the ST0 and ST2 to the adder. The adder will perform the addition between the two registers, and it will push back the result of addition into the top of the stack, which is the original location of ST0. يبقى ST0 plus ST2 will be added together and will placed in the location of ST0. تمام؟ Agree? Make sense? Any questions? طيب. تعالوا بقى ايه نشوف one full program and how can let's demonstrate a full program for the floating point. طيب ادي هنا assume that I want to do this by product or dot product. I want to multiply the 5.6 by 2.4, multiply 3.8 by 10.3, and I want to add this result of multiplication to this result of multiplication, add them together, okay, and get the final answer. Assume that these values are stored in the memory, okay, into the variables. I will call them, I will give them names, the labels, data 1, data 2, data 3, data 4. Okay, so how can I write a successful stack-based program in floating point to perform this operation? You can see here I have float, fmul, fadd. Those are the three instructions used in this code. So the first instruction here, assuming that my top of the stack is starting at the register, I'm originally ST, and ST0 is pointing to the register R5. Okay, but this is my original location. I am in the ST0 is pointing at R5. Okay, you see here the programmer does not have to know the location of the top. If he like the absolute value of the top, he does not have to care about that. طيب الفيرست instruction here is float. float هتعمل ايه؟ احنا قلنا float بتعمل push. يبقى in the first instruction here float value 1 means I have to go to the memory at value 1, load the data and push it into the stack of registers. يبقى ST0 have moved from R5 will be moved to R4, and the data will be stored. الداتا اللي هي 5.6 will be stored. يبقى ST0 now is pointing فين? Is pointing at R4. Are you following? Is it clear? طيب. Then the next instruction is fmul value 2. fmul value 2, that I'm giving only to the fmul, I'm giving only one operand. That means the other operand by default is ST0. يبقى ST0 okay is the default operand اللي هو ST. تمام؟ طيب الfmul بتعمل ايه؟ It should take it will pop the value of ST0 from the stack, go to the value 2, get it from the memory, send them to the multiplier. Multiplier will multiply them and will get me the result of multiplying 5.6 by 2.4, and will push the result back into the same location of ST0 into the stack. يبقى the result of multiplying 5.6 by 2.4 اللي هي 13.44 will be pushed back into the same location اللي هو 13.44 فين في الار 14. Agree? Make sense? Then next instruction, floating point load, another load here, okay, for value 3. تمام؟ يبقى another push will be happening to the stack, okay, will happen here. This is not shown here, okay. يبقى الvalue, let's show that. Books. The value 3.8 will be pushed here. Okay. يبقى هنا يبقى after the second load here الvalue 3 بقى اللي هي 3.8 will be loaded فين؟ will be loaded into the new top of the stack. يبقى ال top of the stack have been moved from R4 لل R3 after the second F load. Okay. يبقى 13.44 is still stored in R4 وال 3.8 is stored in R3. This is after the F load. طيب another F mul between ال value 4 اللي هي ال 10.3 and the top of the stack. Where is the top of the stack? The top of the stack right now is pointing فين؟ مين متابع معانا؟ عند register R3. يبقى this is the top of the stack right now. This is ST0. يبقى at the second F mul here the value 4 اللي هي ال 10.3 will be multiplied by the top of the stack اللي هو 3.8. Okay, and the result of 3.8 multiplied by 10 will be stored at the top of the stack اللي هو ال 35.14. Okay, يبقى the first multiplication result is in R4 which is ST1. The second multiplication اللي هي 39.14 is stored in the R3 اللي هو ال ST0 right now. Okay, after the second multiply if not. Agree? Make sense? يبقى this is step number C. طيب then the last instruction is F add with ST1. F add with ST1, as we mentioned, the default is ST0. يبقى ST0 is involved in the operation اللي هو مين؟ register 3 39.14. Okay, will be added to the R4 اللي هو ST1. This will be added to this. Those two values will be added. يبقى ST0 will be popped, will be added to ST1, and the result will be pushed back into the top of the stack اللي هو ال ST0 اللي هي في الفاينل result اللي هي ال 52.58. Agree? Make sense? Is it clear? Do you understand how the coding here? يبقى the style of coding for floating point is stack based. يبقى I'm not using the memory stack, I'm using a stack of registers. And the operations are involving pushes and pops automatically. The default register is the top of the stack اللي هو ال ST0, and I can use either another operand in the memory or in another ST register. Exactly, because it will pop the ST0, add the value of ST1 and push back into ST0. Agreed? Each instruction, each mathematical instruction has pop and push, pop and push. Okay? Only the load instruction has only push, only the store instruction has only pop. And all the other instructions involving pop, then push, pop, then push. Yeah. You can change that. There are different addressing modes here, okay? So if you are providing only one operand for the floating point instruction, that means automatically it will be using the default addressing mode, which contains pushing and popping with the ST0. Okay, but you can override that, as the example that we mentioned here. هو ده الexample ده I already provided the two operands. Okay. So there is a significant flexibility in the addressing modes for the floating point instructions. Okay, I'm not always have to provide two operands. I may provide one operand or two operands. Okay, there is a significant amount of flexibility here. Okay, that's why we have a lot of opcodes. Tamam? Right. This slide is just explaining in words all the steps that we have just demonstrated here. Now, this is give you some feeling, some sense of how the floating movement is being performed, and we will elaborate more into that, inshallah, in the lab. Whoever taking the lab will see some programming, but we don't, again, in the theory, no programming for floating point. In theory, no programming for floating point. I will not give you a programming example or questions for floating point in the theory. عشان بس الناس تبقى مطمئنة. Okay. Here we need to emphasize on the understand how the X87 is working. Okay. Get some information about the types of instructions, and most importantly is the how the other registers, as we will explain shortly, are working. Fine. What kind of instructions that we have here? As you can see here, some instructions are for integer, and these are actually to load some value as an integer, then convert it to floating point, and then perform the floating point operation for them. This is the BCD. Forget about it. The most important or the default instruction set are the floating point instructions. As we mentioned, all instructions here are prefixed with the letter F to indicate that those are going to the X87. Okay, we have what's called the FLD, the floating point load, FST for storing, floating point store. We have FST and FSTP. FST is not doing popping by default, but it's actually reading from the register only. But FSTP is the one that is actually popping and incrementing the pointer of the stack. We have F exchange, plenty of instructions. We have also conditional instructions. Actually, the instructions for floating point can be divided into subcategories. We have data transfer, basic arithmetic. We have trigonometry instructions. We have logarithmic instructions. Floating point here can do a very complicated set of instructions. We are in a CISC machine, فاكرين? Okay, so the instructions here are complex. Okay, this actually gives you an idea about the set of instructions here that you can do for floating point. In addition to the simple addition and subtraction, multiplication and division, you can do also a complex operations. Like what? Like the trigonometry. You can get the sine, the cosine, the tangent, the arctangent. Okay, all of those instructions are being implemented in the instruction set for the X87. Okay, so X87 can perform scientific mathematical operations. You can get the log, you can do exponential, scaling. Okay. Exactly. Okay, a lot of operations. So that's that you can see here a floating point pi. Where is this instruction? You have a specific question, Ahmed? Okay. So this is just to give you an idea about the instruction set of the X87 and how it is complex. Don't remember any of this. I'm just giving you an idea about how complex the instruction could be, and how powerful is this kind of coprocessor that is attached to the main processor. That's why we leave this processor busy with its real complex mathematical operations, and the control unit here is kind of simple to just manage and manipulate the operations. So how to control this processor is through two registers. I have what's called the status register and the control register. And those, what we wanted to spend the next half an hour explaining for the X87. Do we lose more and more accuracy every time we perform an instruction? It's not necessarily. Remember that we have a very strong representation for floating point, and you definitely lose some accuracy, but remember that even for the single precision, you have significant, how many bits do you have for the single precision? If you are using a single precision, how many bits for the mantissa? Okay, أنا عارف إن كله 32 bits, total 32 bits. I'm talking about the significance of the number. Bravo, it's not all even like 23 bits, it's 24 because we eliminate one of them. مش كده? Okay, so I have 24 bits for my number. This is a significant precision for the number. And if you believe that your mathematical operations needs more accuracy, don't go for the single precision, go for the double precision. Okay, the last slide here is actually talking about that. I jumped, since you asked this question, to jump to the different representation that we have for this processor. This processor X87 can support 3 floating point representations. The two well-known presentations of IEEE اللي هم كانوا single precision floating point of 32 bits that have 23 bits of fractional mantissa, 8 bits for the exponent, and 1 bit for the sign magnitude of the fractional mantissa. It also supports, if you believe that you have a scientific operation and you need a significant accuracy in your numbers, don't go for the single precision. You go to the double precision. The double precision have total of 64 bits for the number, including 52 bits for the fractional mantissa. Okay, 11 bits for the exponent and 1 bit for the sign. Okay, if you are sending rocket to the moon, you may use this double precision. By the way, I'm just kidding, but actually some mathematical operations need even higher accuracy than that. So you can go to what's called the double extended precision for floating point. In the double precision of the floating point, you will be able to utilize all the 80 bits of your data registers. Okay, in this presentation you have actually 63 bits for the fractional mantissa. You have let me just check, you have here 13 bits for the exponent. Okay, so which is plenty of precision. This is very accurate. Okay, very accurate. تمام. يبقى you are not, if you believe that you are worried about your accuracy, don't go for a single precision, go to the double precision or even the extended double precision. The machine is supports a very accurate numbers. Okay, you can go into very infinitesimal fractions and you can representing a huge numbers. Okay, you can imagine, you can go and use the range of values for an 80 bits. Remember that the registers the bank of registers that we are talking about here, the data registers here احنا اتفقنا ان هم كام؟ 80 bits صح؟ Still remember that? We talked that they are 80 bits. However, you may not use all of the 80 bits. You can adjust the machine, tune the machine, okay? So the machine or the processor is working through different modes, okay? So I can set the mode of the X87 to a single precision. So that means only 32 bits will be used of the registers. Or I can set it as a double precision. So that means a 64 bits will be used. Or I can extend it to the maximum, which is the 80 bits. يبقى not all of the bits of the registers are being used. It depends on the mode of operation. It depends on how you adjust the machine. The machine is reconfigurable. The processor is reconfigurable. You can configure it and change the configuration while you are doing the calculations, as we will see shortly. And how can you control all of this? You are doing this through the what we call the control register. Okay? تمام? طيب, let's go directly to the control register since this comes away with our discussion. The control register, okay, is actually allow me to do some calibration, مش calibration يعني configuration for the processor. تمام? What kind of control or configuration that I can do for the processor? I have now we are discussing the control register. I jump to the control register, I will discuss it, then we'll go back to the status register. Okay, since the questions have come, so now we are in slide number 31, explaining me the control register. The control register, I want you to know three major things in the control register. Okay, three fields. The first field is what we just discussed. Okay, how can I control which precision do I need to run the processor now? Okay, this is done through two bits called the precision control, PC. PC here stands for precision control. How many bits for precision control? I have 2 bits for the precision control. So those 2 bits will indicate if I put in those 2 bits in the control register, the value 00, I am in a single precision mode. If I put the value 01, I am in a double precision mode. If I put the value 11, I am in the extended precision mode. So I can run the processor with the 32-bit precision, 64-bit precision, or 80-bit precision, which is the highest accuracy for that processor. How can I do that? I can do that through the precision control bits in the control register. The control register that is a 16-bit صحيح, but okay, it is by changing the value of those bits, I can control the mode of operation for the machine. أول mode of operation اللي هو البرسيجن بتاعتها. احنا بنشتغل, are we working with the X87 as single precision or double precision or highly extended precision or extended double precision? This is controlled through the PC field اللي هم 2 bits, البيتس number 8 and 9 in the control register. Okay, controlling those 2 bits will control. Reserved is reserved. Reserved, that means if you it is something that is reserved for the manufacturers themselves. Okay, it's not for the end user to use it. Okay, يعني don't put it in the 1-0 mode. Okay, this is for testing, for verification. It's not for you, not for the end user. يعني ما تحطش في البي سي عمره الفاليو 1-0. Okay, the processor will not behave as you expect. This is just for testing. It's not for you. It's not for the end user. Not for the end user. تمام؟ طيب. The second thing that we want to talk about in the control register اللي هو ايه بقى؟ السكند field اللي هم البيتس 10 و 11. Those called the RC bits, surrounding the control fields. Okay, and here as we just mentioned, we have to do rounding for the numbers. Do you still remember the example of addition in the last lecture? Okay, the microprocessor, the X87, is doing rounding through the mathematical operation. It has to do rounding. Definitely not in all the cases. If you are consuming all the bits, okay, you are not trimming the number with zeros. انت عندك 23 bits even for the single precision. عندك 23 bits for the fractional mantissa. Okay, are you utilizing all of them ولا you are trimming them with 0 0 0 0 0? لو عندك 0 0 0 0 there is no rounding. But if though your numbers have this accuracy, okay, or needs this accuracy and consuming all of the bits, during the addition and subtraction, you may do rounding. Now, what fashion of rounding here? Okay, there are actually 4 fashions of rounding. Something called rounding to the nearest or even, rounding toward down or minus infinity, rounding toward plus or plus infinity, or chopping truncated. These are 4 different ways to round the numbers. Okay, we will not go into the details of that or the mathematical meaning of any of these, but I just want to highlight that the rounding here is controlled by the end user, because there are different fashions of rounding here. And this rounding is, by the way, is used extensively when you switch from one precision to the other. Okay, because actually you can switch your processor while it is running from one precision to the other. Okay, so here the rounding is being used extensively. Right. The third thing that we need to discuss about the control is the masking. Okay, the exceptions means the errors while doing calculations. There are many types of exceptions for the floating point mathematical operations. We can summarize them in the following, okay, 7 types of exceptions. When you send the instructions and the operands to be executed to the functional units of the X87 machine, there are more than one type of exception could happen. These exceptions could be precision exception, okay, could be underflow, could be overflow, divide by 0, denormalized operand, or invalid operation or operand. تمام؟ يبقى I have here كام؟ 2 4 6 6 different ways, or we can call them kind of errors that happens while the mathematical operation is being performed. Okay, the number could be I may have underflow. Underflow means the results of the mathematical operation is smaller than what I can carry in the register. I am representing the number smaller than the smallest number that can be representing in the representation that I have. So me as an end user, do I want to know about that or not? It depends on my configuration. Okay, if those bits of masking, if those unique bits, if the bit equals to 0, there is no action that will be taken if the exception happens. If the mask is 1, that means I may call some code, okay, to recover from exception or to inform the end user about the exception. Okay, to configure whether I wanted to take action with the exception or not, this is configured by either setting one of those bits or more to either 1 or 0. 0 means I don't want to know about the error. 1 means please tell me about the error. تمام كده؟ طيب, what action will be taken if there is an exception? This is different story. يبقى البيتس ديت is only to either mask or unmask whether there is an exception or not. وضحت الصورة؟ يبقى those bits for the control register is controlling whether I want to inform the end user about the exception or not. 0 means I don't want to inform him. 1 means that means the processor should inform him. And it is configurable by the end user. You can set all bits to zeros. That means no matter whether you have a exception or not, don't tell them. The programmer who decides this is the programmer. So there is a default طبعا للcontrol register, okay? And you can reconfigure that, okay? You can set some of those bits to 0 or to 1 to indicate to the processor, telling the processor, if you have an underflow, please let me know, okay? So the exception will be raised for underflow. If there is an divisor by 0, please let me know, okay? So here you are configuring whether the processor telling you about the error or not telling you. Right? Okay? Those are the 3 things that we need to know about the control register, okay? The PC, the RC, and the masks for the 6 different types of exceptions that can happen. Precision means that precision mask here indicates that the operation is performed in a single precision. يعني انت you are using a single precision mode, but the operation needs a double precision. Okay, so the exception mask will be raised, and so on. Denormalized number. You got a denormalized number, so he have to tell you or not. It depends on you. Right. How could I know whether my operation goes healthy or not? This will be يعني the processor will tell you about the status of the mathematical operation in the status register. If I have another register to tell me the status of the processor. ما بتسأل can we have a number and round it to the four rounding cases. Slide 32. لا مش فاهم سؤالك يا مها. I have a number. لا examples ما بديش examples لأن احنا we will not go into that. This is out of our scope for this course. This will be too much. معلش يعني مش عشان حاجة عشان I don't want you to. We can do this offline بقى. يعني ممكن بقى نقعد مع بعض اللي له interest إنه يتعلم أكتر في الموضوع ده. We can go and we can have maybe an extension, but not for this course. Information is already too much. I just want to give you the minimum, okay, to get you some time. If you need to read more about that, you can go to the manuals for the X87 and read, okay, what are the different rounding and how it works and when to use each type of rounding, okay. يعني هنا في بحر بقى احنا we are just giving the introduction, okay. I'm giving you some information about the X87. But if you want to spend, if we have time to spend more time on the X87, sure, definitely we will explain all of this. I don't want to flood you with too much of information. Okay? This will take significant amount of time from us to explain all of this. So I'm just picking the most relevant, the most important things, and you definitely, everything is open for your further readings. Okay? So I'm more than happy to help you to in a further reading into that, okay? But I want to not to obligate this to all students for this course. Right. The last thing that we need to know about for the X87 is the status register. يبقى احنا اتكلمنا عن الكنترول ريجستر. الكنترول ريجستر will allow the user or the programmer to control three things. Okay, الprecision. Okay, working in which mode of precision. Okay, الrounding والmasking for the exceptions. اتكلمنا, we mentioned that we have 6 different masking. طيب, when the masking, when the exception itself will happen, okay, where the microprocessor or the X87 will tell me about it. يعني الcontrol bit tell me whether I want to know about the exception or not. طيب, if there is an exception, ال X87 هيقول لي فين؟ هيقول لي في الفلاجز بقى بالظبط كده. الفلاجز دي اللي هي الستاتس ريجستر. The status register here for the FPU status register is similar to the status register that we learned in X86. But this is definitely way much complicated. This is way much complicated because now I need 6 bits for the 6 new exceptions that we have. خلاص؟ خلينا نبتدي بيهم اللي هم دول. يبقى I have 6 exception flags. I'm in slide number 25. I have precision error, underflow error, over the same 6 bits or the same 6 exceptions. Okay, do exist in the status register. In the status register, flag equals to 1 means the exception truly happened. Okay, and flag 0 means the exception did not happen. Yani you do a multiply. If you are interested to know whether there is an underflow or not, you will go to check mean an underflow flag or error flag فين في الستاتس ريجستر. ده لو انت اساسا كنت عامل الايه الكنترول ريجستر فلاج بتاعه بيساوي 1. لو الكنترول فلاج equals to 0, yes, this flag will be 1, but it will be kind of a useless. لانك ايه اليوزر will not be informed. There is no action taken if the exception will happen. طيب, يبقى the status register is used for the X87 to tell the end user about the status of the machine. Okay, the first 6 flags are for the 6 exceptions that we have, and then we have what's called مين بقى؟ عندنا ايه تاني؟ عندنا الاكسبشن الستاك فولت. اوكي، عندنا الفلوتنج بوينت بيزي فلاج، التوب التي او بي اللي احنا اتكلمنا عنه اللي هم ال 3 bits for where I am is actually reserved here اللي هم البيتس from 11 till 13. Okay, conditional code flags, I have 4 conditional code flags. Okay, اللي هم C0, C1, C2 and C3. They are occupying the bits 8 و9 و10 و14. Okay, I have error summary status flag, I have stack fault flag, and I have the exception flags. Okay, we talked about the exception flags اللي هم 6 bits دول. Okay, give me information about the successful operations. Okay, whether the operation have any mathematical operation has any of those exceptions or not. طيب, what else we need to cover here? Okay, we need also to explain the busy flag. What's the busy flag? The busy flag, remember that there is a significant difference in speed between the X86 and the X87. Okay, if the X86 taking 1 cycle to perform addition or subtraction, the X87, do you imagine or you can anticipate that it will take 1 cycle to do floating point addition? No, definitely no. The floating point numbers take longer time, take more number of cycles to perform compared to the integer. The floating point unit is much more complex and they are taking much more time to be executed. Okay, remember that the X86 fetch some instruction, recognize that this is a floating point, send it to the floating point unit, and return back to the main program. Will he proceed? ما يقدرش proceed. He have to wait for the floating point unit to indicate to him that it is done, it's finished its execution. The execution for the floating point instructions will take multiple cycles. So actually, the busy flag is raised to 1 as long as the floating point unit is still in its calculation. And once the calculation is done, the flag will go to 0, indicating to the X86, now I am ready for the next instruction. You understand? You get the point? فهمنا البيزي فلاج بيعمل ايه؟ طيب let's move to the next set next flag next bits اللي هم مين؟ التوب فلاج. طبعا فهمناهم دول ايه؟ Those are just 3 bits to indicate where is my top of the stack of registers is pointing to. دول سهلين. صح؟ يبقى top of the stack pointer. طيب الكونديشنال كود فلاجز، ايه هم الكونديشنال كود فلاجز؟ مين شاطر يقول لي ايه كونديشنال كود فلاجز؟ يعني مش يعني انتسيبيت، يعني فكر كده ايه الكونديشنال كود فلاجز؟ What are the conditional code flags? Okay, I have 4 flags, 4 bits. اسمهم C0, C1, C2, C3. Okay, those are for the conditional jump instructions. Okay, so those are actually representing what are the flags that we used for conditional jumps in the X86. حد فاكر؟ we use the carry flag, the 0 flag, أيوة كده, the sign flag, the overflow flag. Okay, so those are something analogous here for the X87. Okay, so those are 4 flags to support the conditional code for the conditional operational in the X87 processor. Okay, so we have a conditional operations for floating point. Right. What else? We have what's called the exception summary status flag اللي هو الفلاج اللي اسمه ES اللي هو bit number 7. البيت number 7 ده is very simple. If any of those 6 bits are raised to 1, okay, this flag also is raised to 1. So it is kind of simply an O-ring between them to indicate that I do have an exception. طيب يبقى from the ES flag I know that there is an exception. If I want to know the exception happens in which type, I will go to these 6 flags. تمام كده؟ Agree؟ لا I'm explaining what's ES. ES is simply doing O-ring between those 6 flags. طيب ايه الاورنج هتعمل ايه؟ يعني معنى كده if any of those flags is 1, the ES will be 1. ليه؟ It is kind of indicating that I have an exception. It's telling the user I have an exception. If you want to know what is the exception, go and check the 6 flags to know which exceptions have happened. Okay? Agree? Make sense? طيب يبقى احنا كده we explained the status register, we explained the control register, we explained the data registers and how they are being accessed as a stack. We shed some light about the different instructions and how complex they are for the X87 machine. I think that's it. We covered everything throughout this chapter. We definitely, this is just maybe ABC in X87. There is a lot of details that needs to be discussed. If you are interested to learn more about this floating point processor, okay, plenty of manuals and user guides that explains each and every bit of details inside that processor. But I don't want to flood you with too much of information about it. The information included here in these slides are more than enough as a jump start for you if you are interested to learn more. By finishing this set of slides, so we have finished the floating point. We have two other sets of slides, one for the interrupts and one for the input-output. We will finish them, inshallah, in the next lecture, okay? And on Thursday, which will be the last lecture in the course, as well as the quiz. The quiz, I'm not sure. Shall we do it right after the class, like maybe at 10:30 next lecture, or we keep it at 5? Because I send an announcement to make it at 5. So I received maybe one request from one students to maybe just shift it to the lecture. Okay, if you prefer to leave it at 5 as it is, I have no problem. Makes no difference for me. Okay, so let's leave it at 5, inshallah, on Thursday. No problem. It will not be that long. At maximum, it will be maybe half an hour maximum. Yeah. Okay. So these set of slides for floating point are not included in the quiz. Right? These set of slides, quiz involving floating all the previous set of slides for the floating point representation, the floating point arithmetic, and the floating point range of values only. Okay, this set of slides for the floating point, the X87 slides, are only included in the final exam, not in the upcoming quiz. The final exam is on 18th. The final exam is on 18th, not on 17th. Okay, originally the university had scheduled 2 times for the final, one for section 232 and one for section 230. And I already sent a request, and they indicate to me that it's already set to be 18th. So is it 17 for all of the students, or it is 17 for some of them and 18 for the others? شفتوا بقى؟ يبقى هو it's not up to date. The final exam is on 18th, not on 17th. I already sent to the university indicating to them that to merge the 2 sections together in the final to be on 18th. So maybe they didn't perform that. I will go and double check. It should be 18, okay? Should all be on 18th. The exam will be on campus. It's better for you. It's better on campus. It's better. Believe me, it will be better. Okay. I have good news about the coming on campus. Okay. If you are coming to campus, you will be surprised. You will have a surprise. Good. Exactly. Okay. On campus, you will have a possibility for backtracking. Yes, you are here. Sure. Okay. So on campus, okay, the restrictions for cheating is less because you are physically here. Okay. So you will be more relaxed. Unless you want to cheat, حاجة تانية بقى. You want to stay at home cheating. طيب. Let's talk about that in the next lecture. خلينا نخلص إن شاء الله in the next lecture we will finish the last two set of slides, which are very small. They will not take too much of the time, and then we will talk about what material will be included in the final. Actually, you have enough of time till the final, so everything should be included, but we may skip some material, maybe. I'm not sure what kind of things that we can skip, actually, because the information is kind of built on top of each other. I don't see a reason for that, but let's discuss that in the next lecture. Yes, the exam will definitely could be open book and open notes. I believe so. That's actually what I usually to do, what I used to do. شفتوا بقى؟ اون كامبس معاك الكتاب وكله جميل. تمام؟ اوكي؟ طيب خلاص. So let's stop recording here. Thanks a lot. We are done with the lecture today, and wish you the best of luck. I want to leave you with your rest of the day, and see you inshallah on Thursday. Thank you. Thank you. Good luck.